Hello, everyone. I'm Jifei from iPad, Shanghai Jiao University. This talk will introduce our work, MT squared, memory bandwidth regulation on hybrid NVM DRAM platforms. According to Intel, when an application is run in different environments, its performance can vary greatly. This is because there may be noisy neighbors in the environment. This causes other applications in the same environment to suffer a significant performance impact. In this case, the ability to identify noisy neighbors and limit the hardware resources they can use becomes particularly important. Thread-grained bandwidth monitoring is the key to figuring out noisy neighbors. With the advent of NVM, memory architectures have now become more complex, and the problem of noisy neighbors has become more complex too. NVM has many good features, such as high speed, byte addressable, and non-volatile. However, NVM and DRAM are currently installed on the same channel, resulting in mixed memory traffic and making the memory interference model more complex. The first challenge is memory bandwidth asymmetry. On NVM DRAM hybrid platforms, different memory access, that is DRAM read, DRAM write, NVM read, and NVM write, use different maximal memory bandwidth. The actual available memory bandwidth heavily depends on the proportions of different kinds of memory access in the workload. Thus, it is no longer appropriate to assume a systemic maximal memory bandwidth and disregard the difference between different memory access like in prior work. Especially, the maximal NVM bandwidth is usually relatively smaller than DRAM bandwidth. Besides, we find that different types of memory access interfere with each other differently, making it even more difficult to estimate the available memory bandwidth and the various workloads. Thus, the assumption that all memory access are equal does not hold anymore. The second challenge stems from the fact that NVM shares the memory bus with DRAM on existing NVM DRAM hybrid platforms. On existing hybrid platforms, NVM traffic and DRAM traffic are inevitably mixed and difficult to separate. With a mixed memory traffic, monitoring different kinds of memory bandwidth on a per-thread basis become almost impossible, which invalidates existing hardware and software regulation approaches designed for DRAM. The third challenge is inadequate hardware and software mechanisms for memory regulation, as both NVM and DRAM are directly accessible by CPU node and store instructions. Counting and throttling each memory access is impractical for the sake of performance. CPU vendors such as Intel provide hardware mechanisms to regulate the memory bandwidth. However, the bandwidth restriction is coarse-grained and qualitative, which is insufficient for precise memory bandwidth regulation. Some other approaches, such as frequency scaling and CPU scheduling, may provide relatively finer-grained bandwidth adjustment. However, they are also qualitative and slow down both computation and memory access, thus inefficient for the overall platform performance. That's all about the background. Next, we will introduce our analysis and several observations about this problem. We analyze severe bandwidth interference problems in hybrid memory platforms and obtain some observations. The first is that the impact of memory interference is closely related to the type of memory access. For example, if we run an NVM read application normally, it can reach a maximal bandwidth of 35 gigabytes per second. However, if we run the same NVM read application and 100 gigabytes per second DRAM read application simultaneously, the throughput of the NVM read application will decrease to 25 gigabytes per second. If we replace the 100 gigabytes per second DRAM read application with a 10 gigabytes per second NVM write application, the throughput of the NVM read application will be severely degraded to 12 gigabytes per second. It shows that tasks that occupy a smaller bandwidth may have a more significant impact on other tasks than those with a larger bandwidth. This observation indicates that the ability to distinguish between different bandwidth types is vital on hybrid platforms. This example also indicates that bandwidth interference level cannot be represented by the total bandwidth. The third is that RAM accesses affect other tasks more severely than DRAM access. NVM writes can lead to severe interference with minimal absolute bandwidth, followed by NVM reads and finally DRAM access. In other words, applications that write NVM a lot are more likely to become the noisy neighbors and affect others. After the analysis and observations, we will introduce the design of our system. The overall architecture of the system is divided into two parts. The monitor is responsible for obtaining information on bandwidth and interference level, and then passing the information to the regulator, which uses this information to determine whether it needs to intervene and how to regulate the bandwidth. MT² can currently be used for 3 different use cases, namely noisy neighbor suppression, memory bandwidth allocation, and cloud SLO guarantee. We will first introduce each part of the system, and then take the use case of noisy neighbor suppression as an example to describe how the system works. The details of the remaining use cases can be found in our paper. First is the monitor. The per-thread memory bandwidth monitoring. We need to get 4 different types of bandwidth as the granularity of the thread. After testing a number of hardware mechanisms, we found that the NVM read bandwidth and DRAM read bandwidth of per thread can be easily obtained via PMU. The NVM write bandwidth and DRAM write bandwidth are not directly available. Meanwhile, Intel NVM can help us to get the total bandwidth. That is, the remaining 2 write bandwidths can be monitored separately for the 4 different types of bandwidth as long as we can get one of them. If we can trust the applications, we can rely on the applications to report their VRAM write bandwidth faithfully. Then we can get the DRAM write by subtracting the other bandwidth from the total bandwidth. If the environment is untrusted, we choose to use PEBS to estimate the write bandwidth roughly. The detail about PEBS can be found in the paper. Even given the accurate bandwidth usage of 4 types of memory accesses, it is difficult to determine whether the bandwidth interference occurs and the severity, since both the decrease of memory access demand and the presence of noisy neighbors can cause an application to utilize less bandwidth. Fortunately, we find that memory interference level can be represented by the latency of the memory access. Instead of indicating memory interference via memory bandwidth, MT² proposes to indicate the interference level by measuring the latency of different kinds of memory accesses, which is supported by the observation that the memory access latency is negatively correlated to the bandwidth. After introducing the monitor, let's take a look at the regulator mechanism. Intel MBA is one such hardware mechanism, which reduces memory bandwidth by inserting a certain latency into memory access operations. However, we find that the granularity of the regulation is very coarse and almost ineffective for NVM accesses. We therefore choose to further limit the bandwidth usage by adjusting the CPU quota, that is, the upper limit of CPU time that an application can use in a given period. Cgroup exposes interface via files in a pseudo file system called cgroup-fs. MT² follows the same approach as other cgroup subsystems. Specifically, an administrator first mounts the subsystem and creates a new directory in the subsystem mount point. Then the administrator writes the PID of the process to the cgroup.procs files. 3 more files in the directory can be read or written to manage the group. First, the priority file is used to get and set the priority of a group. 2 priorities are currently supported. Groups with high priority will not be restricted by the regulator, while the low priority groups will be limited when interference occurs in the system. Second, the bandwidth file is read-only and retains the bandwidth of a group for the next second. Third, the limit file is used to get and set the absolute bandwidth limit of a group. When any one of the limits is exceeded, the group will be throttled. The values take effect immediately. When we use MT² in the use case of noisy neighbor suppression, we first use a monitor to get bandwidth and latency information. Then we use the latency information to determine if there is bandwidth interference in the system. If there is no bandwidth interference in the system, we wait quietly for the next period to come. If there is bandwidth interference in the system, MT² will look for the NVM intensive groups among the low priority groups. And if so, it will consider these low priority NVM intensive groups as the noisy neighbors, and then limit their bandwidth by reducing their CPU quota. If there are no priority NVM intensive groups, the MT² selects DRAM intensive groups and first reduce their bandwidth usage by adjusting their CPU limits values. If the NBN limit has reached its maximum value, it will further limit its bandwidth by lowering its CPU quota. Next part is the evaluation. Our tested configuration are shown as follows. We have two NUMA nodes with a 28-core CPU. Each NUMA node has 6 Intel Optane persistent memory. All experiments are conducted on one NUMA node. First is an experiment about accuracy. PCM is a software that can monitor different types of bandwidth of the whole system. When there is only one memory-intensive program in the system-wide bandwidth reported by PCM is almost equal to the only program's bandwidth. So we run 4 FIO simultaneously to generate different kinds of workloads and compare the bandwidth monitored by MT² with those of the PCM, since Intel also uses PCM's bandwidth as the baseline. The results are shown in the table. While the results reported by MT² are very close to the ground truth bandwidths. We measure the throughput or the execution time of some programs with or without MT² to evaluate the performance overhead. As shown in the table, the overhead is negligible. This is because most operations in MT² are performed by the dedicated kernel thread. We run YSSB on RocksDB as a high priority application along with 4 FIO tasks with different types of memory traffic as a low priority tasks. The 4 low priority tasks perform read or write operations on NVRAM or DRAM respectively. The tail latency is shown in the left figure. Lower is better, and the right figure shows the throughput of the low priority tasks. Higher is better. MT² can optimize the latency of the high priority application and improve the throughput of some low priority applications by only restricting the bandwidth of the noisiest low priority application. This is thanks to the ability of distinguish different types of memory bandwidth. In some scenarios, cross-NUMA accesses are inevitable. A NUMA and NVRAM-aware scheduler can mitigate the memory bandwidth interference via more advanced scheduling policies. For example, isolating DRAM-only applications and the NVRAM-intensive applications to different NUMA nodes. MT² prefers to limit groups with massive NVRAM writes. However, these groups are not always the culprits of memory bandwidth interference. Accurately identifying the noisy neighbors remains a challenge and might require more hardware assistance. We leave the exploration of accurate bandwidth monitoring and regulation with hardware modifications as future work. Our work also has some suggestions for the design of other NVRAM data structure and software. Since NVRAM bandwidth is low and has a more severe impact on overall bandwidth, we need to minimize memory footprint, especially for NVRAM accesses. When designing high-performance NVRAM structures and systems, when scalability is poor, it is worth measuring the overall bandwidth to see if the bottleneck is due to bandwidth contention. To conclude, memory interference problems become more complex and severe on the hybrid NVRAM DRAM platforms. While pulse-rate bandwidth monitoring is the key to reduce memory interference in the hybrid platforms, MT² is the first comprehensive system to regulate memory bandwidth on such platforms with thread granularity. Evaluation shows that MT² can effectively regulate the bandwidth among applications with nearly zero performance overhead and can be used in multiple use cases. At the same time, high-performance NVRAM data structure or software design needs to consider bandwidth interference more to obtain higher performance. And that's all. And thank you for listening.